Good afternoon, and welcome to the General Research Colloquium here in Morristown. And I want also to welcome those who are listening by high-tech remote vision in Piscataway and Navesink. I'd like also to let those people in these remote locations know that there is a hot phone in your room there somewhere. It's probably white and it's wired directly to this one. So at the end of the talk, if you have questions, please pick up the white phone and when the time comes, give us the questions. It's my great pleasure this afternoon to introduce to all of you my friend John Hopfield. I won't tell you how old a friend John Hopfield is. John is now professor of several different subjects at the California Institute of Technology, among them biology and chemistry. Are there any others? No, that's enough. And his subject this afternoon is artificial neural networks and speech processing. I'm glad to have the slide here on the on display because I tend to forget these things. So I need to tell you a few words about John Hopfield. Except for James Michener and Michael Dukakis, John is one of the most famous people that ever graduated from Swarthmore College, which is where I met him. And we were undergraduates together with Mike and achieved distinction and John and I went on to graduate school at Cornell. And then later on, I became a postdoc for John working at Berkeley, University of California in Berkeley. Now I tell you all of this connection with him in part to bask in the reflected glory, but also because I learned a lot about him during these times, but the most startling thing I learned about him, I learned when I was a postdoc working with him at Berkeley. And I had to work especially hard, very hard, incredibly hard. I had to run all day and all night just to try to keep up with where this guy was carrying me with his problems and experiments and things like that. Now, John was at that time a theoretical physicist, but he became, in order to help me, an experimental physicist and taught me a great deal about experimental physics. The most important thing I learned, however, was that there are not just factors of 2 and 3 separating the abilities of different people. There are really orders of magnitude. I discovered that there's a person in this world that just does things I can't even imagine. Now, at that time, we were working on solid-state physics, and it didn't take a lot of intellect to work on solid-state physics. You just worked out the consequences of one thing after another. And I was rather disappointed that my friend John, with his ability, was working in solid-state physics. I don't think I ever communicated this to him, but I had grander plans for him. That he should not be a solid-state physicist all his life, that he should really go on and do something fantastic, because there aren't very many people like him in the world, and he has a responsibility as a result of that. Now, I'm happy to report to you that he has heard my prayers, and he has stood up underneath all these responsibilities. He has satisfied my needs. I'm not doing this. He's satisfied my needs many, many times in shifting his attention from the field of solid-state physics into various areas of biology, looking at genetic code, some of the problems involved there, and then finally the subject, not finally necessarily, John, I don't mean, this is not the end, but the subject that he will talk about this afternoon, neural networks, are very often in the countryside around referred to as Hopfield networks, and for very good reasons, because John has discovered, has worked on their properties and brought them to our attention in a way that I think has changed the way we look at computation, the way we look at artificial intelligence, and I think this is a most important contribution. I'm proud of you, John. I'm glad you're here, and welcome.
Oh, thank you, John. It's from time to time I did worry about whether I was going to have any remaining hour myself, but it is so marvelous to be introduced by somebody who's been a friend for so long, somebody I remember admiring so much. At Swarthmore, where he was this guy who he understood what physics was about, and I sure didn't in that second of my sophomore year. And a member of the 4 chipmunks, weren't you? 4 squirrels?
Squirrel and his nuts.
Thank you. Oh, it is very nice to be here. What I'm going to talk about, just sort of list how the talk's going to go. First, I'm going to just try to describe why it is that some people, whether visionaries or lunatics, you can make up your own mind, are interested in artificial neural networks. Going to talk about what artificial neural networks are from the point of view of electronic circuits. Address a little bit how artificial neural networks compute and how they can be programmed, or that is to say, set up or designed to solve particular problems. I will then turn to speech as an example of an interesting problem which can be put on such networks, I think perhaps in a useful fashion, and we'll use speech to talk some about what it is about artificial neural networks which seems to make them effective in computation. And then finally, I will turn a little bit at the end toward artificial neural network technology. Let me start with the question then of why people are interested in this subject. Well, there are, of course, did I lose does the screen want to be down, or is that a decent thing to slow? Okay, okay.
It comes from behind.
Ah, all right, all right. Now the screen does not want to be down. Thank you, John.
We could ask it.
Right. And the other question is there some kind of pointer? Finger, all right. All right, that's a real neural network. The brain with the outside case removed. This is the kind of thing that real neural networks do. For example, well, here's one, a thing which people work on very much these days is trying to get artificial systems to do something in the way of speech understanding. Thank you, John. So here's the kind of sentence which people who work on AI have no difficulty whatsoever in getting machines to understand. This is a very simple sentence. If you diagram it the way you would have in the 8th grade, its meaning is utterly trivial. But since you don't normally work with speech by diagramming sentences, you have a lot of difficulty with this. My secretary had an awful time typing it. And in some sense, it's not a sentence in the English language because nobody would either utter it or understand it as somebody else did. On the other hand, the kind of thing that we deal with, so this is fine for machines. Machines are very good at diagramming sentences, and once you do that, the meaning of this is elementary. Whereas you can look at this kind of sentence, pair of sentences. In a physics audience, it always takes a few seconds to remember what a fruit fly is. Obviously, this is a much harder problem because you bring everything from your understanding of metaphor on the one hand and understanding sort of the thing, the way nature behaves on the other, to understanding these simple sentences. Or, oops, no, that's the wrong thing to do. Simple problem. You immediately recognize George Washington. Now, you've seen this particular picture on a dollar bill many times, but if I'd put up instead the picture of one of your friends, in about half a second, maybe a little less, you would have recognized that particular person. Now, this is a very powerful computation. And one of the things which is happening today is that computations of this sort, recognizing people or working with real speech, the kind of things which previously only people or animals did well, are more and more being asked to be done on digital machines. And digital machines are by and large not very effective in this area. you can get a measure of the difference between effectivenesses. You can take a problem like multiplication of big numbers. We know that our brain is intrinsically slow hardware. There isn't a clock in a brain, but there's an equivalent time constant of the hardware. You might give it something like 1/100th of a second time constant for most of the processing that it does. You shouldn't penalize, if you want to compare computer structures, you shouldn't worry about absolute speed of the hardware. So it's most useful to speak of the amount of computation that can be done in a clock cycle or in a time constant of the hardware. Now, if you look at VLSI, you can do multiplication of numbers like that in something on the scale of 100 clock cycles. If you ask how long it takes a person to do the same computation, it's something like 10 to the 5 clock cycles. You can do these multiplications on very few devices in VLSI. It takes the number of brain cells that you have as 10 to the 11th. You've got about 10 to the 14th connections between these things. So the number of device clock cycles it takes to do a multiplication in VLSI is on the scale of 10 to the 7th. In neurobiology, it's on the scale of 10 to the 16th. There's a 1 missing there, to 10 to the 19th. So in some sense, VLSI is on the scale of 10 to the 10th times better at doing multiplications than we are. On the other hand, you can go to a problem like face recognition, where you can take some reasonable sized computer, calculate the number of clock cycles you're willing to work with, 10 to the 7th percent. Supposing you work with a PC and try to do face recognition. Well, you might have 10 to the 7th clock cycles per second, and you might be willing to last 10 to the 6th seconds to do a face recognition. You still can't manage to do it, really. And on the other hand, on a brain in 50 clock cycles can recognize somebody. And if you look at the number of device clock cycles, it's simply very, very much smaller. So clearly there are tasks which fit on machines, and if the task fits on a machine, the machine looks extraordinarily effective, and the task fits badly on it, the machine looks awful. VLSI can be designed to do multiplications. We were, in some sense, designed or evolved to do pattern recognition, and the differences are just extreme. But the why artificial neural nets really comes from this fact. You ought to be able to get rid of this ineffectiveness of VLSI if somehow you made things more in the spirit of the way the biological system does its computation. And since that's the kind of problem which you're pushing computers toward, in these days it becomes an interesting problem to approach from an engineering or computer science point of view. Well, what are artificial neural networks? You know, if you look at any particular VLSI chip, this is a little section of the design drawing of a VLSI chip to do something or other. You find all these micro details of wires, transistors, polysilicon, and what have you. There's some effective circuit of this kind of thing, which, given the circuit drawing, you can then draw out the engineering drawing for. Now, neurobiology is filled with this kind of effective circuit also. It just looks a little bit more complicated. There are nerve cells. These are each drawings of a particular nerve cell. The nerve cells in actual neurobiology are densely packed. You need to have, there are techniques by which you can stain individual ones and thus be able to see them in more or less in their entirety and see what their structure is. This is the cell body where the nucleus is and the DNA and what have you. This is an axon from which information is sent from this cell to other cells. These are dendrites from which information comes in to this cell from other cells. Each of these little bumps, which you can see you can see them better along here, this is a better focus, is a place where a contact is made between the input, the information from some other cell is coming in here. And from the number of these bumps, you can quickly see that there are literally a few thousand inputs to a typical neuron in neurobiology. Now, these cells are relatively complex objects, but you can try to capture some of the essence of what they are as far as a computational structure is concerned, and that is done in this slide here. Neurons typically communicate with each other by a pulse-coded scheme, and the firing rate, that is to say the rate of output of pulses of a particular neuron, tends to be a sigmoid function of the total input to a cell. And it saturates at one end and it simply turns off at the other. So the essence of neurobiology is a few things. It's cells with a sigmoid input-output characteristic, which can be thought of as amplifiers which saturate. It's a large number of connections, the synapses of neurobiology, which you could think of as being the outputs of some amplifiers are connected to the inputs of others. And then there's also a general integrative feature. The response of the system isn't instantaneous. Cells have a lot of capacitance for the same reason that chips are slow in some sense. They're slow because you always have capacitance. You've got to charge the capacitance before voltages can change. For similar reasons, neurobiology, which is filled with membranes which are only about 100 angstroms thick, also has lots of capacitances. And so the general set of equations of this system is an integrative set of equations which essentially expresses time rates of change of something in terms of inputs. The circuit then to be thought of in terms of artificial neurobiology, and the one from which John had this, the drawing made for the title slide, consists really of something like this. There are amplifiers which have sigmoid input-output characteristics. These amplifiers put out outputs which make effectively resistive connections to the inputs of other amplifiers. And the peculiarity which I've put in here is the idea that an amplifier can either be normal or inverting. You can get both kinds of outputs, because in neurobiology you know that you have cells which are excitatory, which when they're active tend to drive other cells. You also have cells, different cells, which are inhibitory. When these are active, they tend to suppress the activity of other cells. And to carry that over into the electrical analog, one needs to have amplifiers with a two-sided output. So that kind of circuit, if you had, in addition, resistive and capacitive input impedances to these amplifiers, is really what an artificial neural network is about. And the equations of motion of it are very simple. This just describes the rate of change of the voltage on the input capacitor in terms of an external input, which I haven't written down, the charge which leaks off the capacitor through the input resistance. And this term has to do with the fact that amplifier J may be connected to the output of amplifier J, which is this capital V, may be connected to the input of amplifier I by a conductance, Tij. This simple set of equations with sigmoid input-output characteristics is the set of equations which I'm going to be talking about all the rest of today. It's a parody of neurobiology, but it is the chief embodiment of artificial neural networks as they're thought about today. Now, I don't just want to work with arbitrary circuits of this sort, because I could obviously manage to take elements of this sort and capacitors and resistors and build a cray. But I don't want to deploy my elements that way. I want to ask, what are the essential features of neurobiology, the qualitative features, and deploy the elements in that fashion? That's what makes artificial neural networks rather than simply digital computers. So let's look at some of the qualitative differences between VLSI and real neurobiological neural networks to understand what features we want to bring over into electronics if we're going to speak about artificial neural networks. Look at first the question of connectivity. If you look at the typical transistor in VLSI, it tends to get inputs from a few others and make outputs to a few others on the scale of 3. It is rather typical. Whereas in neurobiology, that number tends to be on the scale of 3,000. If you look at the connectivity pattern in VLSI, it's very much generally conceived as feed-forward information flow. So these transistors get information early, which is passed on to these, which is passed on to these, and so on. If you look at the way that neurobiology is organized, there's an immense amount of feedback in the system. For example, in vision, well, you got the retina. You have a first stage of processing whose name I will not bother you with. I will. It's called the lateral geniculate body. You have to learn something today. Then you have the second stage of processing, primary visual cortex. Information flow is obvious. Retina, LGN, visual cortex. And yet, since you can look at where the axons are, what the axons are doing in neurobiology, you can ask about the information flow. And there are more axons bringing information back from visual cortex to this first relay station than there are information leads going forward from that relay station up. It's an immensely fed back system. Well, the general mode of operation, if you look in VLSI, the whole circuitry is conceived around the idea that there are going to be stable times at which various leads are high and low. Wires are carrying, in some sense, binary information. If you look in neurobiology, a particular axon has going out along it a pulse-coded thing, and the amplitude and the frequency of that pulse-coded arrangement is actually used as the information. You convey analog information along an axon. The digital system is essentially conceived of with a clock. Neurobiology is much more run like a set of dynamical equations, like the equations of classical electromagnetic theory or classical mechanics. Well, there are capacitances, there's the intrinsic time constant, there's delay. In the case of the electronics, delay is always the enemy that just keeps you from running the clock faster. In the case of neurobiology, it turns out that these delays can be used as a virtue. They can be used to organize the information to help you compute. And the final thing is that the neurobiology actually changes its intrinsic architecture in learning, whereas in some sense you have a very different kind of thing which goes on. You think of a digital circuit as being a fixed entity. Well, all of these things, I'm not going to talk very much about how to do learning, but you can see that all of these top things really are items which you can perfectly well put these into the kind of circuit elements that I've already described, and these are what are going to be emphasized in the artificial neural networks. Now, how can we get these things to compute? Let me talk for a moment about what computation is. Here is a simple drawing to try to describe digital computation and neural network computation in the same picture. I'm going to describe what you call batch mode processing, where you have a program and some data and you want to get the answer. How do you describe that kind of processing for a digital computer? Well, the idea is very simple for a digital computer. There are a whole bunch of logical variables in the machine. And every clock cycle, the machine goes from some logical state to another logical state in which some of the ones have become zeros and others of the zeros have become ones. And the entire flow of one logical state to a next has been determined completely by the machine designer. And so what there is a space of logical states of the machine, and there's a movement through that space which has been determined by the designer. And what you do when you do a computation in batch mode, your program and the data describe the starting point in this logical space. You start somewhere from the initial information and program, and then the pathway is then completely determined, and you go along, and after a while the machine stops. It stops because it's gotten to the answer, and it prints out the answer for you. And so the idea of a computation in a digital system is there's a flow which has been determined by the machine designer through this state space. You start somewhere, you go to a point at which the computation stops, and that's the answer. There's nothing in this idea which necessitates having a digital space. You could just as well have an analog state space characterized, say, by the voltages on the input capacitances of all the amplifiers that I was describing for an artificial neural net. In which case you could describe batch mode computation in the same fashion, and the initial information will put you somewhere, and all the connections will determine a set of dynamics, and you'll move along. And if it's going to get you an answer and stop, you want to have the answer be a stable point so you can read it out. But you can use then the same description of computation for both systems. In this picture, you can also understand part of the hazard of moving away from the digital paradigm. Namely, that one of the important things of digital computation is the idea of restoration, that you make hardware inaccurately, that there's noise in the electronics, but that a 5 or a 4.5 or a 5.5 volts on a certain point is regarded essentially as being all equivalent, a logical true in the next operation of the machine. The operation of the circuitry restores values, so if you only have reasonable 10-20% fluctuations in voltages, you don't accumulate any errors at all. There's a restoration. See, ordinary analog systems, which are high gain, and it turns out that these neural network systems have to be high gain systems, have the difficulty that if there's a little bit of noise or imperfection, it's a high gain system and it tends to get amplified, and so you wind up somewhere which is nowhere near where you wanted to be, where the answer is. And you've got to have a process of restoration which keeps moving you back onto the right path in order to have the system able to do something in the long run interesting. Digital designs have that automatically, and it's one of the things we want to look out for in these analog systems, is to understand how the restoration gets there, and to make sure that therefore we can build real systems which are noisy, which will be able to compute useful things. But that's what computation is from the point of view of a neural network. If I want to have stable points as answers for batch mode computation, and I want to make neural circuits to do this, electronic circuits, there are two different styles I could immediately go to. One of them is a feed-forward network where the outputs of amplifiers go to the input of another set of amplifiers and go to the input of another set of amplifiers, and where there are no feedback paths. This obviously has no stability problems. I put a set of voltages here, and in the best of all possible worlds where there are no spurious feedbacks, then there will be stability, and I'll get a set of voltages out here very quickly as the system relaxes. This system is one which is very popular for certain learning paradigms. This feed-forward network, which has no difficulty with stability, is one in which you can learn a set of input-output relations quite effectively. There's work going on here in that regard. A great deal of the work is following the work of Rummelhart, Hinton, and what's the third? Williams on an algorithm which they developed and which goes back in time to more and more obscure people, but it's a way of programming a feed-forward network of this sort to do particular tasks. There's another class of systems which is, on the one hand, much harder to deal with, and on the other hand, which is more powerful computationally, based on getting stability through feedback. As you know, the most likely thing to happen with feedback is oscillation, but there are some circumstances under which feedback simply gives you nice stability. Circuits of this sort have much more interesting dynamics than these circuits do, and therefore can do more powerful computation. They are, on the other hand, harder to program. That is, it's harder to learn sets of connections to do useful things. I'm going to talk for the next little while about networks of that sort. And then finally, as I move on to speech, I'm going to be working with systems which are not as simple as either of these. Speech is not a batch mode problem to begin with, and going to have to be just generalizing things a little bit. But it's very useful to understand some of these building blocks on the way. Feed-forward networks is things which are obviously well-behaved, and the idea that some feedback networks might also be well-behaved and will be computationally powerful. As far as the feedback networks are concerned, there are many circumstances under which the feedback networks will be stable. But one of the simplest of them is a case where a network is symmetric and where the output of amplifier I goes to the input of amplifier J with some conductance strength, and the output of J goes to the input of I with the same conductance strength. So it's a reciprocal network of a certain sort. A network of that sort turns out to have behind its dynamics a function which always decreases in time. And if it stops decreasing in time, it means that all the voltages have stopped changing. That serves as a kind of potential function for the motion of the network and guarantees that what will really happen with this network is no matter how you start the thing out, the voltages will evolve and go to a stable state and stop changing. And so this network, which is symmetrically constructed, will be something which you can use in batch mode computation if you can begin to control the stable points. Well, how complicated is the stable point behavior? If the stable point behavior is too simple, it'll be a trivial network. It's easiest to understand what the stable points of this system look like in a high gain system. No, all right. I'm sorry, before going on to high gain, this shows in 2 dimensions the dynamics of a network with stable states, so that no matter where I start, I follow one of these trajectories and I wind up at a stable state and stop. And in general, if a network has dynamics of this sort and is made as with only stable states as its characterization, it will have behind it some kind of effective energy, a computational energy or a Lyapunov function on which it is sliding downhill. And this is our way of understanding why it is that that pattern of stable states exists. And it's obviously much easier to understand and to visualize terrains of this sort and their consequences than it is to have to remember detailed maps of that sort. And it's very useful then to use this energy function as a way of understanding networks which have stable states, feedback networks which have stable states. If you look in the high gain limit and you work with amplifiers whose maximum output is 1 and whose minimum output is -1, by the high gain limit I just mean the sigmoid of the amplifier gets very abrupt. Then it turns out that the very odd term that I wrote in this energy function, in which all of you will have looked at and sort of groaned because it made the situation look complicated, absolutely goes away. And the only effect it has is to restrict the output voltages to between 1 and -1. And then what actually happens is that the motions of the system turn out to run to a minimum of this simple function on the hypercube. Hypercube because I got n amplifiers and if I have an n-dimensional space that I'm talking about. These t's are the connection strengths, those i's are the inputs, and I simply go to a minimum of this on the hypercube. And with trivial exceptions, the minima turn out to be on the corners. So what really happens is every amplifier is going to go full on or full off, and the stable states of the system are going to be determined by something which looks like this, where each of these mu's is plus or minus 1. Every physicist has been brought up to look at that and say, Ising model. And you all know, if you read physics today, about the complications of and the joys of the spin glass and then the rich mathematical structure of the minimum energy points of the spin glass. And so it tells you that a neural network, an amplifier network, has complex connections, so the connections aren't stereotyped, is going to have a very rich structure of minima and is therefore capable of doing a fairly rich amount of computation. Now, there's another importance, incidentally, to the high gain limit, and that is, of course, that if we're going to try to make things which are compatible with, say, digital output, having things which are a high gain limit so you get digital output is very attractive. Now, there are a great variety of things which you can do. Associative memory is one of the first things which I've worked on in this system, because associative memory is just a very natural thing for such networks. I will just remark on why it's natural and not show you anything at all really about associative memory. See, if I store your names in a digital computer, I'll normally store them, well, look, at heart, if you look at what memory is, memory in digital machines is always by address. And if I store John Worlock and I remember Worlock and I want to know the first name, unless I know the address at which I stored Worlock, I have no way of getting John out other than by searching through all the database. Of course, you could say, well, I'll hash code things. I'll use Worlock to generate the address. But then if I happen to know John and was looking for the last name, I couldn't do it. And in general, memory by address says you really have to know the address. Whereas, our memories of things are just of a totally different nature. We know a very vague set of facts about something or other, and when we need to remember it, we are reminded by a subset of that set of facts, and any reasonable subset is actually capable of allowing us to find that memory. And the way that you can see that that's related to the systems I've been talking about is to think about associative memory, or think about some things you can easily quantitate. Say height, width, height, weight, age. Set up 3 Cartesian coordinates, and any particular person you know then is this particular location in this space. And so there are a few points for the few people you know which are your friends. And if you're given height and weight, you can see, well, I just go to that point. There's nobody else with that same height and weight, and I can read the age out. And so if you're given but right there you see you've made use of the idea that if you're given approximate or partial information, what you want to do is sort of move to the nearest thing in that space and go to those axes and then read out the coordinates of the axes, and that's going to give you the real information, the rest of the information about the system. So the whole idea of an associative memory is very much like one of these flows. This is shown in 2 dimensions, but where having partial information puts you somewhere, and if you just coast along the natural flow, you'll come to the actual location, and the axis values will then be the appropriate answers. And so associative memory is not some wild thing which you have to spend time learning how to structure. It's a natural consequence of working with information in this kind of network, and where the information stored is actually stored in the strengths of the connections between the different amplifiers. Associative memories of this sort have been simulated, have been built, and they have some marvelous properties which remind you of the way that your memories work on a much higher level. But I am not going to indulge myself and talk about associative memories. We're going to fast forward through all kinds of things so that I can actually talk about speech, which is what I promised to talk about. Before turning to speech, though, I will at least talk a little bit about how one can use the energy function to program. And as an example, I'll take the problem which David Tank and I produced to just see how you can begin to use these energy function minimizing networks to compute things. Supposing you want to make a circuit which is going to take in an analog voltage V and digitize it. Well, most of you say, I'm not an electrical engineer, I really don't know how to do the problem. I've already taught you how to do the problem today. You all can design the circuit. It's very simple. When you want to digitize this analog voltage, what you really want to do is to pick a set of numbers, V0, V1, V2, V3. Each of those is 0 or 1. And I want to have a voltage written this way so that this voltage is as close as possible to the voltage which I'm trying to digitize. That's what you mean by digitizing this analog voltage. Well, one way of stating that is to state that I could take this actual analog voltage and I could subtract this quantity, I could square it, I could say what I want to do is to minimize this quantity. I want to pick these VNs each to be 0 or 1, in such a way that I minimize this quantity. But this is exactly what one of these networks will do. If I run it in the high gain limit, each amplifier will go to the rails, and if I pick amplifiers which have maximum outputs 1 and minimum outputs 0, and I use one amplifier for each of these VNs, then that aspect of the problem is satisfied. This is a quadratic function of these VNs, and in fact, this describes all the connections in the network. You can then go from that within one common scale factor and build the network, as David Tank did. The network turns out to look like this. These are the conductance values at the various intersections, and now you put in an analog voltage here, and you get the digitized voltage out there. And there are a large number of problems which you can put on networks in this fashion. Some of them you can find exact answers to. Others of them you can find pretty good answers to quite rapidly, although you don't actually find the best answer. David Tank and I again worked on the traveling salesman problem, a problem of finding a shortest path between a set of cities. You can put this kind of problem on a network. You know that the actual finding of the shortest path is a very hard computational problem. The system that we described will find a very good path, not necessarily the shortest path, very rapidly, sort of sliding downhill on its energy surface and finding a local minimum, and the local minimum is really very nearly the global minimum in many of these problems. If you work with a simple problem in which wasn't very hard, you know, like putting the cities around the perimeter of a circle more or less, then the system will find the best answer. In a general problem, however, it finds only a very good one, but it does it very, very fast. And of course, that's a lot of what biological computation is about. It isn't that John Worlock can be awfully hard to recognize if I can do it in 50 clock cycles. It's just that there's an awful lot of data which has to be chewed on, and it's obvious that if there's some crummy algorithm, he's an overpowering amount of information, and that algorithm, which is designed to be fast, and designed on no other principles at all, can take the immense redundancy of information there is in his face and still manage to get all the information out in 50 clock cycles. To realize how redundant the information is, remember that he constitutes perhaps 10 to the 8th bits of information as I look at him, and yet if I take a Hirschfeld diagram, 5 lines would be sufficient to do the recognition. All right, let me turn now to speech. What does this one say? Yeah. David Tank and I got to thinking about trying to find a real-world problem with real-world variability to examine these networks on. There's a great, if you can make up your own problem, you can always make up problems which the networks can do. I mean, that's not hard. But obviously what these problems do in the biological world is to solve real problems, and there's some real problems out there which from the point of view of artificial intelligence or computer science or the telephone company, which you might like to be able to solve. And problems which, look, work in speech, your dog can recognize words in speech, so it isn't a uniquely hard thing to do. And it's very important to work on a problem that you know a real neural system can solve. You'd also like to have the problem well defined all the way from input to output. You'd like the problem small enough that you can do a thorough simulation of it. And you might even be greedy enough to say you'd like to have a potential use for a $10 chip which would do this kind of thing. And so we have been working on the problem of small vocabulary continuous speech. Uni Krishnan has joined us about 9 months ago working on this. David and I had probably been working about another 6 months or so before that. So I'm going to talk now about a problem of trying to recognize words in continuous speech from a neural net viewpoint. Let's first sort of look at the computational problem. Somebody says we. Well, there's a pressure wave as a function of time. Lasts about 0.2 of a second. And you would like at this point to make a decision that the word we has just been said. or if the pressure wave was different from this, but the word we has not just been said. And if you're going to do this with a neural net, an artificial neural net kind of thing, it really means that there's going to be some amplifier or some set of amplifiers which has got to be switched on at this point for a brief period of time. That's what's going to symbolize the recognition. Well, all right, that's the problem. Now, speech is a fairly stylized waveform. And roughly speaking, it's convenient to try to describe the problem by saying that speech at any particular time you could think of as looking like one sound or looking like another. And there are only, there might be a few hundred different ways speech could look in any particular little 10 or 20 millisecond time bin. When you say a particular word, you could think of it, for convenience, as a sequence of syllables, a sequence of little identifiable pieces. And these identifiable little pieces are only a few hundred in number. Now, unfortunately, there are some problems. If somebody says cat, well, the duration of different parts of the word can be stretched out or shrunk, so you can have extra symbols put in or symbols deleted. The next thing is that you realize that everybody is going to pronounce words somewhat differently, and so there isn't complete accuracy in what symbols occur in these different locations. And the final thing is that there are no such thing as words. If you think back to the first time that you heard French or Spanish spoken, and you had the 6 weeks quick course in it, you heard it spoken by a native speaker and your mouth hung open because you just couldn't hear the words. There was this continuous sound stream coming by and no indication whatsoever that it wasn't just one long word. You say the quick cat took the bacon, and you realize that the places where you pause aren't at the beginnings and the ends of words. And that's one of the major things which makes this problem hard. And we began working on this problem in particular because we realized that neurobiology has an elementary solution to that problem available. That solution is already known to the mustache bat, and it's also known to various radar and sonar engineers. You see, the problem is, first of all, you've got to take information which occurs over a whole period of time like that and concentrate it somewhere on some amplifier which is going to turn on or not turn on. You have to concentrate it in space so that the right amplifier goes on, and you've got to concentrate it in time so that information over this entire place arrives at the amplifier which is to turn on or turn off. Well, the place that you see this problem most clearly in biology is in bat sonar. See, a bat has an elementary problem. You'd really like to locate, say, a mosquito out here, so you put out a pulse, and you want to get a pulse back and indicate how far away the mosquito is, do by timing, find out the range. Now, this is what you'd like to do, but this puts a mosquito's a small thing, get very little reflection and power back. In order to get enough signal to detect coming back, you're going to have to put out a very high peak power if you're going to do it that way. And a bat can't do it, and your local electronics engineer also complains when you ask him to do that. You go to your engineer and he says, I'm willing to give you a pulse which looks like that. Now you get back this, and you have to start doing some signal processing to do precise timing between this little thing and that, and it's a little bit awkward. And see, already if this lasts 1/100 of a second, it corresponds to 10 feet, and that's not very good for hunting mosquitoes. Well, one way out of it, and a way out which is used by the mustache bat, is to chirp the pulse so that, except it's ultrasonic, and then you get back this, and you could use a down sweep or an up sweep. I don't care whether the frequency goes up or down with time, but I do want it to change, and I do want to know which one of these is being used. Because then the bat can have neural hardware of the following sort. You know that early in hearing, the hearing process, if they'll find some neurons which respond to some frequencies and others to others, there's a spatial map of frequencies. Or if I look in one place in the spatial map, I find low frequencies, and the frequencies just go up continuously as I move to neurons in a different physical place. And so there's this physical map of neurons here, our low frequency, here our middle frequency, here our high frequency. there are propagation time delays in neurobiology. And if I were to say use a slow propagation path here and a fast propagation path here, and a cell here which is connected, gets inputs from all these, you could see that if I worked with a chirp which went from down to up, this would get activated first. So energy would start moving out along here, and at some time it would have reached halfway along. Whereas at this point, the highest frequencies are just now arriving. They start here. And so this shows you where these things are in space at some particular time. But now if these are slowly progressing and these are fast propagating, this will go up like this, and all these pulses will arrive and activate this neuron at the same time. In short, we can use time delay to organize the information, and so that we can detect, we can just get a strong, sharp pulse from this chirp because we know what structure the chirp is going to have if we get it back. And in exactly that same idea, but in a more symbolic fashion, you can certainly use in speech. Since we know the structure of the words that we expect to hear, that's the only reason we can recognize words. If you don't know the words, there's no way you can pull words out of continuous speech since you can't tell where the boundaries are. When you can tell words in real continuous speech, it's because you actually know those words. So we're going to have a system where, like the bat, we know what to expect to be coming. We know what the words are. The problem is to milk them out of the data. And we can use this kind of time delay to organize the information, and so that features which are detected at different times in the sound stream can organize themselves and go over and activate some particular recognition amplifier. We also see that as far as the bat is concerned, it doesn't make any difference whether sonar information came in before this pulse or not, because it won't, if I just say they have a continuous frequency stuff coming in, it won't get organized into a sharp peak. And so stuff which comes beforehand and stuff which comes after doesn't matter. The bat doesn't have to know when the pulse is coming back. The whole idea of word break is something which you never have to address. This shows a drawing of an electronic circuit which David Tank made. We actually at this point are doing computer simulations of a much larger circuit which is done in the spirit of this one, and so I put this up just to remark on what the various parts are. Automatic gain control, which turns out to be more or less irrelevant. A set of different frequency filters, simple two-pole filters, spaced from about 150 cycles to about 3 kilohertz. This is the kind of, and then there's a short time averaging and rectification of the outputs of these. Available here, then, are outputs which correspond very much to outputs which we know are available in the early part of the auditory system in all mammals, namely a spatial map of frequency, a cell or an amplifier which responds to one frequency but not to another. Then from there, it goes into feature detectors, which look at these different frequencies and on a short time scale make a decision of, roughly speaking, what the pattern looks like. And I will show you what that looks like in real data a little bit further on. Then there's a set of delay lines which correspond to the axons and can be done just by RC filter type things. And then resistive connections, synapses, to various amplifiers which are supposed to be recognizing different words. And then cross connections between these amplifiers, a fed-back system, to embody the simple idea that you should not at the same time recognize two different words as having just been completed. Just to give a little bit of indication of how this goes, this is the outputs of the set of filter banks, 32 different frequency units, when digit 0 is spoken or when digit 1 is spoken. Those of you who are quick will be able to see that those are different, but gee, those differences are not very big. You put this through a first simple kind of neural processing for features just simple amplifiers which are high gain amplifiers and connected up in an elementary fashion. And then that same output, which I just showed you before, becomes this and this. And you'll immediately see, you'll immediately see there's now no difficulty in recognizing the difference between a digit 0 and digit 1. Digit 0, for example, digit 1 never has power in these frequency bands, and digit 0 does. And there are lots of detailed differences you can just see by eye. Now, unfortunately, the eye is an infinitely powerful calculating machine compared to what we're going to follow this with. But nevertheless, you can see that there's enough here that you can get your teeth into, whereas if I just worked with the raw data, there wasn't. And one of the essential things, in our view, and I think in the view of many people at this point, is that you cannot ask neural networks simply to learn anything. When you have some understanding of what the problem is or how biology should go about it, you design as much as possible as that in. And that's what we've done here in a reasonable set of feature extraction from the previous slide. Now, these simply go into delay lines. The delay lines have all kinds of connections to other amplifiers. And at this point, we learn by a massive amount of data what those connections should be to do word recognition. This shows some of the actual kind of sound waves you wind up working with. What is spoken here is 675, and you can see the pressure wave as a function of time. And you look at this and you say, sound power, lots of sound power here, little sound power here. That's obviously where 6 ends and 7 starts on and so on. Not true. You can this is the Fourier spectrum of the same thing, the power spectrum. Unfortunately, these time bases aren't the same. That corresponds to this here where there isn't much power. But this silence here is actually on the interior of 6. 6, if spoken alone, would end about here and look about just the same as this looks. 7, if spoken alone, would start here and look like this. It isn't that the words simply butt up against each other. The words simply overlap like this. And silence is no indication at all of where words break. This is the kind of thing you're up against. The network has no difficulty doing this. This shows some particular digit stream being spoken, and these are now the outputs of the different amplifiers as a function of time, and as this corresponds to digit 0, digit 1, digit 2, and so on. And you can see that what was spoken was 0, 2, 7, and so on, and each amplifier simply comes on. With 99% accuracy, this system, the simple system, will work with single speaker, continuous speech information and really solve that problem. It's not an interesting problem. The interesting problem is to try to extend this to multiple speakers. The interesting thing about this, and this is what we're about to start on now, the interesting thing about this is to see that there is no word break problem. Continuous speech is simply no more difficult for this system than isolated words would have been. I'd like to comment just briefly on how well the system is doing, how big it is. This is little enough total hardware that you could easily get it on a single analog VLSI chip. Now, I'm certain that you could get digital hardware to do this same problem on a single digital VLSI chip. One interesting thing in this problem is how little work this system is doing. It's all sort of pushed along by the incoming sound pressure wave. There is no clock or anything. And except for the frequency filters, which have to, of course, work at the frequencies which are being driven it with, for all the rest of it, the electronics only has 10 millisecond timescales. So that you could obviously do a problem like the speech word recognition problem 10 to the 4th times faster and still be able to solve it on this amount of hardware. And I think that would be pushing people a little bit in the digital regime. Now, where does this system actually get its computational power from, if you believe that it really does have some? There is a feeling in the trade that somehow, it's really because of the use of analog. Analog adds are free. Look, I have a wire, and I simply put different currents into it, and suddenly the currents all sum going down the wire, and that's instantaneous. That's also untrue. It always takes time for things to settle, and when you look in detail, it turns out that these analog adds are slower than it would have taken to do the equivalent digital adds. But in order to do digital adds, you would have had to have buses with the digital information on them, whereas with analog adds, you can use these wires to have analog information, and you would have had to have a bunch of junk, lots of digital processing for, say, for a 4 or 6-bit adder, and you can do that without that much hardware. It's an area thing here rather than a speed thing. The analog system here is actually slow. But there are a couple places where you really do get help. One of them is the simple idea of algorithm. So you start out here, not with the idea of trying to generate the best algorithm. Look, there are undoubtedly 10 billion algorithms which will solve this problem adequately. Don't look for the best one. Look for one which is parallelizable. And by pushing yourself into a neural net mode, you are explicitly accepting only algorithms which are very, very parallel. And that's really part of the power of this. So that's why one can manage to do it now on slow hardware, is because we've looked only for highly parallel algorithms. And the last thing, which is, if you want to ask, where does the system get its power from? It comes from using the device physics. It comes from, in this case, from actually using the delays and the fact that you can get RC delays to organize things for you as a constructive thing. And that actually saves you a lot of digital hardware which you would have to otherwise have explicitly made. And I think in general that's going to be true for real applications of these. When you want to go to hardware aspects, if you can use the device physics to your advantage, they're going to look very powerful. Whereas if you can't use the device physics to your advantage, it may be just as well to do special digital hardware to look like neural nets as it would be to make true analog neural nets. Well, in summary, the field of artificial neural nets tries to simulate and or fabricate devices in the spirit of neurobiology, and in the long run to solve useful computational problems of the sort which biology does effortlessly. The relation between the trivialization of digitization and the rich world of analog systems was well captured by Tom Stoppard. In the play The Real Thing, in the early part of it, you'll find an absolutely marvelous diatribe. It begins, "You know the Swiss, utterly reliable, and they've done it without going digital. That's what I admire so much." And it goes on for a while and says they made a few digital watches themselves to draw the Japanese further into the mire and got on with the numbering of the bank accounts. And now you see how the Japanese are busily putting hands on their digital watches. Digital's got no class, you see. And I rather agree with Stoppard. The classic computer, the one which really solves tough problems, is the one that biology has managed to evolve and which we continue to struggle to understand and to emulate. Thank you.
Thank you, John. I don't know if I'm heard elsewhere, so I will go to a microphone. But I'd like to thank you very much for this interesting talk, for being with us, and I would like to open the floor to questions. There is a floor in Navesink. There are 2 floors in Navesink. There's one in Piscataway, but before going there, I would take questions from this room, if there are any. Oh, for those of you from this room who would like to ask questions, please come to this microphone, and those elsewhere, please find yourself a hot phone.
Well, I have an idiotic question to ask. Being a computer science student during the early 70s, we were forced to spend a lot of time studying this thing called serial automatons. The purpose there was similar to yours. The approach is different. We basically operate on a threshold logic, but it's discrete time and discrete space. And the professor that I learned this from, he spent 30 years on the subject after he worked with von Neumann. And my own judgment is that his 30 years of work really didn't resolve the issue for the reason that the approach we took, we couldn't understand the computational complexity of taking a whole bunch of neurons, connect them together. We don't know the right mathematical implication. Number two, we don't know how to program this when you have thousands or more of these neurons interconnected together. My question is that when we go to the analog approach, do you think that it offers a better answer for us in terms of trying to understand the basic mathematics of the biological system?
I too would agree with your assessment about cellular automata. They've been an interesting mathematical structure, but they are things which abstractly can do powerful computation. But in reality, nobody has found out how to map computations onto them. Whereas in this particular class of systems, there are learning algorithms, there are energy function tools, and people have understood how to map real problems onto them and actually begun to solve some real problems in interesting fashions. And the other thing which I think is very important about these systems is that as you model them on biology, you also know that you are getting a fault-tolerant algorithm, so that in spite of the fact that a few % of your devices will fail, the system itself ought to still work. Most of the cellular automaton literature presumes that you have made a perfect cellular automaton.
But I think I still agree with Pat on this. So in around 70s, we also seen people try to approach the human. I seen a guy who came to our university for interview, try to model the human locomotion control. He came up with a system of linear equations, about 100 parameters, 100 equations, and claimed that's the way that control how we walk. And I just couldn't believe it. And seems to me, differential equation is the basis of some of this analog logic, and have some parts of that.
But the important thing is to have a network structure such that you can understand how the computation will work. And I think that's been a fair part of the progress, to understand network structures and learning algorithms and other such things, so you've got some tools. You don't just have a set of equations which you know will solve anything but don't know how to deal with, that you would have, in some sense, begin to have some programming tools for using this kind of system.
Thank you. That was.
Thank you. I would like to entertain a question from Piscataway, if there is one.
Is this a doubt as to the existence of Piscataway?
No, it should just come from the air. I think we doubt the existence of Piscataway. Could we perhaps hear from Navasink?
There's no questions at Piscataway.
Thank you.
There is a question from Navasink.
I'm sorry, would you repeat, Navasink?
Yes, we have a question.
Oh, good. Let's have it.
Question is as follows. In the speech recognition machine that you described, was that a full neural network, or was that simply a thresholding type machine? And the second part of the question is that I know that car telephones are being advertised, which do number recognition so that people can dial the phone while they're driving with both hands on the wheel. Do you know if they're using a similar type of machine for recognizing the telephone numbers?
Okay. The first part of the question was what kind of amplification is being used. The first stage of the processing, we are using very high gain amplifiers, and so they're basically thresholding, and you could see in that trace of the speech having been simply processed, the outputs were 0 and 1 after that. Then those go on with all kinds of analog connections into a final set of amplifiers, which are themselves analog in nature. They're not run in the complete high gain limit. I don't know what kind of algorithms are actually used in the cellular phones. My guess is that the cellular phones are asking you to speak like this yet, using a gap in the speech stream to indicate a gap between numbers. There are also, I know, algorithms which are designed to understand that you are only going to be speaking a certain number of numbers and to try to justify to try to string a string onto the piece of speech which you produce. But my guess is that the cellular phone things are so cheap that they are probably simply isolated word recognizers using the sound power to tell where the word is and then doing a simple template match and not having to solve the continuous speech problem.
Just a follow-up. So if I understand you, then you did not have a full neural network in the speech recognition machine that you described. It was acting more as a thresholding type machine.
The front end of it is thresholding. The back end is really fully analog.
Okay, let's have another question here at Morristown.
I understood what you were saying about how you were using the time delays in order to interpret a bat chirp, which had a falling or rising frequency dependence. I didn't quite follow the thread when you were explaining how you were using time delays to analyze your continuous speech. Could you explain that a little bit again?
Yeah, no, let me give a shot at that. Oops, just buy it. Yeah, all right. Okay, said 0. Well, 0 has the end of 0 occurs at about here, whereas this line here, this highest frequency unit is on at the beginning of the word 0 and off the rest of the time. So we want to have a time delay of about 5/10 of a second between the time that this signal, between the time that 0, between the time that the highest frequency band spots something and the time when that signal actually gets to the recognition unit. Then we have also this same line connected to the same recognition unit with 3/10 of a second delay, but with a negative sign connection. That would mean, for example, that if this signal comes in now here, 6/10 of a second later, it is evidence that the word 0 was said, whereas if some sound power came in at this time, only 3/10 of a second from the end, it would be evidence against 0 being said. And in that way, you can look at all these particular things and compare them with all the other words and understand that some of these are evidence for some things being said, and other places are evidence where the signals, if they were there, were evidence against. The end of a word is here, and so you know what the time delay is with respect to how long you should delay in bringing that evidence forward. And you do all that kind of thing, but using a learning algorithm to do it for you based on a large database, and that's how it works. But you need the delays so that effectively all these positive things get each delayed the right length of time so they all arrive at some point here, all in phase.
Thank you, I understand.
Piscataway, do you want to try now? Okay, let's try once more Navasync.
There's a question here.
Good.
For memory states, have you ever looked at, rather than having, say, minimum energy states, something like quasi-periodic or periodic states, something like chaotic structures?
The question is basically whether we've ever tried to use dynamic attractors, dynamic stable stability, rather than static stable stability as an answer. And that's very attractive computationally because network, in some sense, simple flows to stable points are a very limited form of dynamics compared to having things which have stable limit cycles, chaotic attractors, and what have you. And we are going in precisely that direction at present in our more biological work, where we're trying to understand olfaction, the sense of smell, and where it's very clear that in the earliest stages of olfactory processing, you convert a signal which you think of as being you take a sniff, that's a slowly changing thing. That signal actually generates a 50 hertz activity in the first processing center, and you seem in that system to have a dynamic attractor, and it's what we're working on at present. Much harder to control, of course, because there's much, I have much less understanding of the mathematics of that situation.
Okay, another question from Morristown.
Yes, the brain is a three-dimensional entity. A VLSI implementation is a two-dimensional entity. Is that going to limit the complexity of the problems that we'll be able to solve?
Of course, you know, you can map a three-dimensional structure onto a two-dimensional structure if you're willing to make a large enough two-dimensional structure. But realistically, if you want to go to a system with as many amplifiers as neurobiology has, as human neurobiology, and as many connections, you're going to have to use that third dimension or you're never going to get there. And that's one of the things which actually makes optical implementations of neural nets look particularly interesting. Because as Dimitri Psaltis, Nabil Farhat, Dana Anderson have been doing, you can use a plane of an optical light valve with each resolution element representing a neuron. You can then use volume holograms to describe the connections and feed the system back around, and you can get effectively three-dimensional structure of the connections in the volume hologram. And since connections are the limiting feature, because there are 1,000 times more connections than there are amplifiers, if you can just get that into 3 dimensions, you may be able to really run the numbers up. In the case of VLSI, once again, you might think of trying to run amplifiers on crystal and silicon, and by some other means build a deep set of connections up above those amplifiers. But you do need a third dimension if you're going to go to big numbers. It's, on the other hand, surprising how well a relatively small size system does in some of these problems. If you take something like vision, you're going to have to go to 3 dimensions. Speech is easier, much smaller amount of data, much more two-dimensional-like in flavor.
Let's try Piscataway.
Yeah, sir, I have a question at Piscataway.
Thank you.
You had 32 different frequencies, and you were talking about 10 numbers and a learning algorithm. And I just wondered if you would perhaps say what the future might hold for more vocabulary. How many frequencies would you need? How complicated would the learning algorithm get? Could it be automated, and so forth?
Okay, our learning algorithm is, of course, automated at present. I think that if you want to go to a larger vocabulary problem, you're going to want to go to a network which is essentially hierarchical in nature. You want to have a first layer of things which is working over a short time scale and recognizing, say, phonemes or perhaps syllables, and then working over a longer time scale, something working with syllables and trying to work with words. And at some point, I think you are going to definitely want to go digital. But there's an early sort of signal processing end of this that I think you very much can do in the analog domain. I would certainly never try to think of pushing the analog domain, say in the simple way that we're trying to do it, into a large vocabulary problem. I think that would be a mistake.
Let's try Navasync again, please. If not, let's come back to Morristown.
This is too low. During your talk, you said that the Ising models have a very rich energy structure, and therefore they are a good model for computation. It is the therefore part which is worrying me. For example, if you try to solve a traveling salesman problem, you wouldn't want to have local minima at significantly different energies. Can you expand on that?
Okay. The therefore is connected with the idea that if I take a complicated Ising model, I know that finding its ground state is an NP-hard problem. And on the other hand, finding the ground state is it's a local minimum problem. And so I can see that the networks the Ising model is complicated enough that a hard problem might be able to cast on it. The network may not find a good solution, but at least you can see that you could program. You could write a program to try to do it. Whereas if the Ising model only had 2 stable states, you could never ask a very hard problem. You could never program a hard problem onto it. Now, if you are interested in an exact solution to the salesman problem, this is the wrong way to go. This is the right way to go if you want a crude solution to the salesman problem in 50 clock cycles. And that's what neurobiology is about, and that's what most of biological pattern recognition is about that computer science doesn't do well. And the interesting thing about the Ising model is, from my point of view, is not about the traveling salesman problem, is not trying to find an exact solution, but trying to find, on a minimal amount of hardware, in a very short time, a fairly good solution. You know, recognizing you ought to be an NP hard problem, because I ought to be able to trying all kinds of permutations and so on. But the fact of the matter is, you know it's not that hard, because you can remove most of the data and you can still solve it. So recognizing you is a simple example of what is a hard class of problem. And that's usually what I think biology has. Biology doesn't usually have these delicate little decisions on which you and your twin brother differ by only a freckle. And under those circumstances, it'll get the answer wrong half the time.
Where's next? Piscataway. Okay, next Navasink. Okay, next Morristown.
Hi, Dr. Hopfield. I was wondering, in your digit recognizer, what learning algorithm do you use to reduce all the data into connection strings that the neural net can use to recognize its digits?
Okay, in spite of all the time delays, it turns out you can convert this system to something which looks like a single layer analog perceptron, in which case you get essentially the same set of connections no matter what learning algorithm you use to a first approximation. We used the one that I described about a year ago for learning probability distributions as one which didn't have arbitrary parameters, and one which I thought I understood why it should be that way. But since it's only a one-layer network which we're teaching, it's not critical what learning algorithm we use.
Okay, thank you.
Once more to Piscataway. It's fun journeying around, isn't it? And now Navasink, any further questions? Anybody from Morristown? I have a question. You have a question.
Go ahead, John.
Okay, my question has to do with language recognition, and it seems to me when I listen to a foreign language, and sometimes when I listen to English, I have a tape recorder that I store it for a little while. I can get it back. And when I really bomb out is when I load up my tape recorder and I keep playing it over and over and over again, and I can't take any more in. And I don't, is that related to the feedback, or is this something you can build into your object, or is it irrelevant? Am I crazy?
Those are not mutually exclusive. No, we all seem to have this tape recorder where you hear a word and you don't understand it, but you keep playing it back to yourself, and as long as you don't have to keep on working in real time, you can fish it out. You have to keep working in real time, you're dead at that point. We have no such second pass capability here. It would be nice, because what you would like to do is to use your recognition ability to tweak the parameters of the front end of this thing in an adaptive fashion, so that if you're not recognizing very well, you'll adapt yours so you seem to focus in on better things to recognize with. And no, it would clearly be very helpful. But we're trying, of course, to recognize these digits in a single pass. And if the string of digits exceeds your tape recorder length, well, you're in trouble. But we haven't built a tape recorder here.
Okay, we have at least one more question from Morristown. Josh?
I wonder if you can get that slide back that you just had. That's it. It turns out that in both cases you come off pretty well if you say that there is just sort of one clump in each frequency band at one time interval. Just sort of make a little hump at where most of the activity is. So I was wondering if you could then, instead of doing a learning algorithm which adjusts strengths for each time interval, for each frequency band, just adjust a single time delay for each frequency band.
You'd want to do that in a learning sense anyway, because what you don't know, of course, there's digit 2, 3, 4, 5, 6, 7, 8. If another digit, if 2 has something here also, you may want to kill this connection completely. Or here, where this has got 2 different humps, it's the one of them which doesn't occur in some other word at that point, which is going to be essential. So you really have got to compete words against other words before you know where to connect them. It isn't enough to say where these should go. It's always a competition. And since it's only a one-layer learning problem, the learning is trivial. And you should make use of the fact that that is an available tool. There's no reason that you've got to second-guess it. Though you could restrict yourself to one connection per row and try to solve the problem as best you could that way, rather than allowing a connection at a variety of different places. We'd allowed connections with 10 different time delays. You might say, use only one time delay per row. That's a reasonable thing to try to do, but I would try to select that with a learning algorithm. Incidentally, I should mention that although in the learning procedures always use continuously adjustable weights and so on, by the time you're done, you actually need only about 1.5 bits of digital depth in the connections to get this network to work up at this level.
Well, one last go-round. Piscataway, are you there? Good night, Piscataway. Navasink, further questions? Okay, good night, Navasink. Morristown? Good night, Morristown. John, thank you very much for being with us and for this excellent presentation.